Good day. I hope you guys are all alive and well and enjoying your Calc 3 lecture videos. Um, Now we're going to discuss the properties of the directional derivative. So the directional derivative in the direction of u of f is equal to the gradient of f dotted with u, maybe evaluated at the point, or rather the magnitude of the gradient of f times cosine of theta. And so this new definition can be derived briefly from our directional derivative as a dot product formula. But I'm just going to give it to you and say, hey, okay, we know this is going to be true. The magnitude of the gradient times cosine theta. And in this situation, theta is representing the angle between two vectors. So how can the directional derivative be useful to us? Remember, we thought about the directional derivative as like a contour map, and that those rivers were all perpendicular to the contours, and that the water flowing down a hill is going to choose the shortest path, the way it can get down most rapidly. So in that sense, we could think about this directional derivative telling us about the function, and it increases most rapidly when cosine theta is equal to 1. So we're at that maximum for cosine, which means that theta is equal to 0. And u is in the direction of f. So that's to say that each point in the domain, for each point, f increases most rapidly in the direction of the gradient vector at P. The derivative in this direction is going to be the magnitude of f times cosine of 0, because cosine of 0 is the maximum for that cosine, which is just 1. So we say, or we can leave that intermediate step out and say that directional derivative of f is going to equal the magnitude of f. That's where it increases most rapidly. And then similarly, it decreases most rapidly, decreases, goes down in the direction of the negative gradient f. And so that occurs because we would be considering cosine pi, which is our minimum for our cosine theta graph, which is -1. So essentially, if you are asked where the function is increasing or decreasing at its fastest, so going up at the steepest amount or down at the steepest amount, that is always going to be found by finding the magnitude of the gradient of f. So the positive magnitude for the gradient of f is where we are increasing most rapidly, and then if we negate that, that's where we are decreasing most rapidly. And lastly, that directional derivative, if they are orthogonal, if gradient of f and u are orthogonal, so if u is orthogonal to the gradient, well, we already know that the dot product of orthogonal vectors is going to equal 0. So this is a direction of 0 change in f. So let's look at this in an example. For this example, we are given the multivariable function f of xy is x squared over 2 plus y squared over 2. And does anyone recognize what this is the shape of? What space curve we have here? Or rather, I should say, what quadric surface? And hopefully you are all recognizing that it's a paraboloid, and because these are the same, we know it's a circular paraboloid. So for this example, we're going to find the directions in which the function increases most rapidly, decreases most rapidly, and then also elicits 0 change, has no change, all at this point 1, 1. Before we get started, let's kind of try and visualize what we are looking at here. So I've got my right-handed coordinate system, and we're thinking about this space, or rather visualizing this point in space on that curve. So we have a circular, try and make this, I'm actually going to try and make it a little wider, circular paraboloid. And so we are considering some point on the edge of this curve at 1, 1, 1. So if we think about visualizing a cube here, not perfect, but that cube, we can see there's my point on the edge of that cube. So remember, the directional derivative tells us a derivative in the direction, and we want to know where that derivative is increasing most rapidly, where it's decreasing most rapidly, and possibly where there is no change, where all those directional derivatives would be the same. Okay? So you can see increasing would be going up this elliptical paraboloid, decreasing we'd be going down, and then no change, all those directional derivatives would be increasing or decreasing at the same rate along the edge of this circle here. So let's do our calculations, and then we will be able to visualize that maybe a little better if we can't already. So considering the definition that we presented on the previous slide, we're going to need that magnitude of the gradient of f. So recall our gradient, grad f del f, is partial of f with respect to xi plus partial of f with respect to y j. All right, so we got 1/2 x squared plus 1/2 y squared. My gradient of f, the partial of this with respect to x, so taking that derivative, I'll get x. And then x is a constant, so that will be 0. Partial here, I'm going to get y. And I need the magnitude of the gradient at my point, 1, 1, which gives me 1i plus 1j. So this is my gradient vector. What is the direction of this gradient vector? And so that's going to be u equals I plus j over its magnitude, and the magnitude of this vector is √2. So in this situation, it's increasing most rapidly in the direction of 1 over √2 I plus 1 over √2 j. Where is it decreasing most rapidly? So there's the increasing most rapidly. And by definition for part B, that would be the negation of the u vector. So that would be negative 1 over √2 I minus 1 over √2 j. So that's where it is decreasing. And so these are two vectors just pointing in the exact opposite direction. And so then C, where there is no change in the directional derivative. So that's going to be perpendicular to my u vector, which lets us know we're going to need our normal vector. Remember, we know that u dotted with n, it's a weird n, is going to equal 0. So if I take u, 1 over √2 I plus 1 over √2 j, and I dot that with some vector ai plus bj, that's going to give me 1 over √2 times a plus 1 over √2 times b. And we know that dot product has to equal 0. So essentially, we just need to solve to determine what a and b are equal to. Solving this equation, I have 1 over 2a equals negative 1 over root 2b, or rather a equals negative b. So considering we created a like this, we can say that my normal vector is 1 over root 2I minus 1 over root 2j. And that normal vector in the exact opposite direction would be negative 1 over root 2I plus 1 over root 2j. So let's pull in the picture from the book, which looks a little nicer than what I've drawn, and you can kind of see that a little bit better. So here's our circular paraboloid, and we're looking at this point on the curve. So it's increasing most rapidly in the direction of this red vector. And so the red vector that's drawn on that picture is this guy. That's what we found with that U up here. And my negative U, this is where it's decreasing most rapidly. So that's what we found with negative U. And then the no change, those normal vectors, along this circle around the edge of this circular paraboloid, all of those directional derivatives would be changing at the exact same rate. So there's no change in the directional derivative. They're all slightly different directions because they're at different spots on the curve and they're pointing to different places in space, but they all have the same steepness up the curve. And so that's kind of what we're trying to visualize here. And if you take these vectors and you just transfer them down, decreasing most rapidly is going straight towards the center from that point, or straight out from the center. And then no change is right along or tangent to that circle. If I take that circle and I pull that down to the base here, it actually kind of look a little more like this, but I think you guys know what I'm saying. This line is tangent to that there. All right, so I hope you understand what the idea of a directional derivative is, and why is it important for us to find max and min values for derivatives, because that lets us know where the least and most change are occurring. All right, so cool. Directional derivatives, where they increase or decrease most rapidly. In what direction would they be pointing?